Welcome back to Differential Calculus. In this video, I want to talk about the derivatives of trigonometric functions. Get my head out of the way and we will dive right in. The first couple of rules here, I am not going to take the time to prove because the proof is incredibly tedious and quite honestly, it would take an entire week just to get through and it's just not worth it. But the derivative of sine of x is cosine of x. And the derivative of cosine of x is the negative of sine of x. So derivative of sine is cosine, derivative of cosine is negative of sine. Sine and cosine kind of just ping pong back and forth. It's one of several places that you have come across in your study of trigonometry where sine and cosine are incredibly closely related to each other. There is a way to prove this using the limit definition of the derivative. Like I said, it's very tedious, but for anyone who's going to continue onward, at the end of the second semester of calculus, you will learn another way of thinking about sine and cosine beyond the trigonometric definitions that you're accustomed to. And in that light, taking the derivative of sine to get cosine is going to be very easy to prove. So if you really are anxious and you really want to see how this proof works, wait around for another semester and a half and I promise we'll get there. For our purposes though, I do want to use these definitions to get the derivatives of at least a couple of the other trigonometric functions. I generally don't worry about the whole gamut of trigonometric functions, but sine and cosine definitely are incredibly important. Tangent tends to be useful. So the derivative of the tangent of x is another one that I would like to make sure that we know. We can take the derivative of tangent by remembering the relationship that tangent is sine divided by cosine. And we can differentiate this using the quotient rule. Right? The derivative of the numerator, derivative of sine is cosine, times the denominator, minus the numerator, times the derivative of the denominator. The derivative of cosine is minus sine. That minus will turn the subtraction that's already there into plus, all over the denominator squared. Notice here, we have cosine squared, we have sine squared, and the Pythagorean identity tells us that cosine squared plus sine squared is 1. So 1 over cosine squared of x. Now, thinking through identities a little bit further, the reciprocal identity tells us that the reciprocal of cosine is secant. So the derivative of the tangent of x is secant squared of x. So we've got sine and cosine, which technically speaking, sine and cosine can take care of all of your trigonometric needs. But when it comes to going from polar coordinates to rectangular coordinates, tangent is a very valuable tool there. So now we've added tangent to the list. And because of the relationship that tangent has with secant, which is one that you should be somewhat familiar with already, right? The Pythagorean identity involving tangent says that 1 plus tangent squared is equal to secant squared. So for that reason, it turns out that it's also incredibly valuable to have the derivative of the secant function in your back pocket. So let's clear out a little bit more space. And take the derivative of secant, which we will likewise rewrite using sines and cosines. In this case, it's just 1 over the cosine of x, which I'm going to think of as cosine of x to the negative first power, so that I can use the chain rule. The derivative here will be negative 1 times the function cosine x to the negative 1 minus 1, which is negative 2, times the derivative of cosine, which is minus sine. All right, the negatives will cancel each other out. Cosine to the negative second I can think of as being in the denominator. So I end up with sine x over cosine squared x. There are a couple of different ways that you could simplify from here. The most common is to rewrite this as 1 over cosine x times sine x over cosine x. 1 over cosine x is secant x. Sine over cosine is tangent. And we get that the derivative of the secant is the secant times the tangent. For the sake of completeness, I will also list out that the derivative of cotangent is the negative of cosecant squared, and the derivative of cosecant is the negative of cosecant times cotangent. Cotangent and cosecant come up very rarely, so I'm going to mostly just cross my fingers and hope we never have to worry about those. But they do exist and we can list them. All right. Getting on my math teacher's soapbox for a little bit, I'm fairly confident that at some point before this video has hit its expiration date, before I have to redesign this course, we're going to see a trend in mathematics education that cosecant and cotangent kind of evaporate away and aren't mentioned in trigonometry courses anymore. Because honestly, with modern computing being what it is, they're not that useful. Right? Sine and cosine can do everything. Tangent picks up a little bit of slack to make things easier. Secant is going to still hang on because of its relationship to tangent that we just saw here. But cosecant and cotangent just don't have anything going for them. So it won't surprise me if they disappear over the course of the next few years. For that reason, I don't spend a lot of time on them. You probably shouldn't spend too much time on them, but we can't completely forget about them. The same way that society mathematics hasn't completely forgotten about some of the other trigonometric functions that used to be important, right? The var sign, the Haver sign, the covar sign used to be very important, but digital calculators in the 1980s made those obsolete, and soon modern computing, I think, is going to eat away a little bit more, make trigonometry just a little bit easier on us. For today, though, the important thing is how to deal with these differentiation rules that we've established. And Trigonometric functions are one of the places where the product rule tends to come up most often. It is very common to end up with expressions that do things like x squared times the sine of x. And to take this derivative, we are going to need to use the product rule. The derivative of x squared is 2x, multiply that by sine x. Then add to that x squared times the derivative of sine x, which is cosine x. And it doesn't take that much work, but it is something that uses a rule that doesn't get that much love otherwise. Before I wrap up here, I want to point out one other. And that is something like sine of x squared, which is going to use the chain rule. The derivative of sine of x squared, well, we'll take the derivative of sine, which is cosine, evaluate at the same point, x squared, and then multiply by the derivative of x squared, which is 2x. And then one more, the derivative of sine squared of x. Remember, sine squared of x is the more common notation for what should technically be written as sine x, the whole thing squared. So again, we're going to use the chain rule. The outer function is squaring, so 2 times the argument, which is sine x, times the derivative of sine x, which is cosine x. All right, these three functions at first glance look fairly similar to each other. There's the same sorts of things going on in all of them, but as you look closer, you realize that the differences really drastically change what is happening with the derivative. I very often see issues of students getting confused as to what's happening where. I'm confident in saying that most of those issues come from trying to race through and do things too fast. So take your time, be careful, read the function carefully, make sure you can identify whether you are dealing with something that's going to use the product rule, the quotient rule, or the chain rule, and then proceed accordingly. All right. To wrap up, here's one for you to try on your own. We're dealing with the secant of 2x. This one is a lot more challenging than it seems at first glance. So take your time, see what you can do with this one, and I'll see you in the next video.